Welcome to EDU World Space.
So for this problem of a projectile, let's focus on the motion of the mass center. And this moves as if the projectile has not exploded. So the motion of the system, r bar, or the center of the system, is equal to v naught times t in the I direction minus a half gt squared in the j direction, since that's the acceleration due to gravity. And we have these values, so we can substitute them in. So v naught is 35 meters per second, and a time of 3 seconds has elapsed, times I minus a half times g, which is 9.81 meters per square second, times a time of 3 seconds squared, and that's in the j direction. So we get the motion of the center of this projectile to be 105 meters times I minus 44.145 meters in the j direction. So what we know about the center of mass is it's defined as follows. So m times the center is defined as the mass of each particle multiplied by its position vector Ri. So the sum of the mass times the position vector for each of the particles. In this case, each fragment of the projectile after it explodes. So that's the mass of fragment A times its position vector A plus the mass of fragment B times its position vector Rb. And so we can equate the left and right hand sides. So this is the mass of the entire projectile, 13 kgs, into the center, which is 105 I minus 44.145 J, and that's equal to the mass of A, 5, into 90I plus 7J minus 14K. So that's the position vector after it has exploded and moved off. That's a position vector of one of the fragments. The other fragment has mass 8 kg and an unknown position Rb. So Rb is what we wish to calculate. So if you rearrange this equation, we find that Rb, so if we simply perform the scalar products on either side and then add like terms, we can solve for Rb. And Rb ends up simply to be the position vector of the second fragment, 114.4 meters times unit vector I minus 76.1 meters times j plus 8.75 meters multiplied by the basis vector k, and hence we have a position vector for fragment B.